All right, here we go. So we are going to go through the surface area to volume demo that we conducted yesterday in class. And hopefully I can get you some more guidance and a better explanation about how this occurs or why we actually even look at this. So just kind of a recap, you have on your formula sheet for the AP test, you actually get a bunch of surface area to volume formulas for different shapes. So little geometry reminder, R is radius. So diameter would be all the way across a circle and radius is just halfway, so half of a diameter. Length, height, width, S is length of one side. You can only use that if that's a cube and all of your sides are the same length. And then surface area to volume. Reminder, surface area is going to be just the surface of something. So if you think about a cardboard box, the surface area would be the cardboard. The volume then would include the inside of that shape. So anything that you could fit inside of that box would be considered part of the volume. So those are the formulas. Again, you don't have to memorize them. And actually on your sheet, it says that you won't have to do any sort of calculations with these equations, but you may have to answer questions about how a changing of the surface area of a cylinder might influence the changing of the surface or the volume of a cylinder, or how the ratio of those two things changed based on the shape of the shape, whatever shape you're using. Okay, so this is what we're starting out with. We've got 3 different sized cubes, and we have to do some calculating about surface area and volume. So when you do a cube volume measurement, you have to use the formula S to the third. Remember, S is the length of the side. So our biggest cube was a 3 by 3 by 3. So height 3, length 3, and width 3. So you just have to do 3 to the third, which ends up 27 centimeters cubed. Then the surface area of a cube is 6s squared. So s squared would be 3 squared 9 times 6 is 54. Surface area to volume ratio is just taking these two numbers and turning it into a ratio. So 54 to 27, that actually simplifies really nicely into a perfect 2-to-1 ratio. So twice as much surface area compared to the volume. Our next shape, number 2, was also a cube, but it's a 2 by 2 by 2. And so 2 cubed is 8 centimeters cubed for volume. And then 6s cubed squared would be 4 times 6, which is 24. So you get a 24 to 8 surface area to volume ratio, that's 3 to 1. Shape number 3 is the smallest cube. That was just a 1 by 1 by 1. So you get 1 centimeter cubed for your volume and then 6 centimeters squared for your surface area, a 6 to 1 ratio. So notice that as we get a smaller cube, our surface area to volume ratio actually increases. You have more surface area on the surface of the shape rather, or compared to the volume, which would be inside of the shape. All right, the next shapes that we did was 2 different size cylinders, so you're gonna have to use different formulas for these. The large cylinder, it had a, I'm trying to remember, it had a radius of 0.75 and it had a height of 1.5. The smaller cylinder had a radius of 0.25 centimeters and it had a height of 0.75 centimeters. So you have to plug those into the formula. The biggest cylinder, total volume, you have to use pi r squared h. So you come up with 2.65 centimeters cubed. Surface area, you have to use for cylinders 2 pi r h plus 2 pi r squared, 10.6 centimeters squared. So your ratio doesn't look as pretty when you're working with the cylinder, but it is roughly a 4 to 1. There's roughly 4 times as much surface area compared to volume. The smaller shape, 0.15, 1.57, again, not perfect, but pretty darn close to a 10 to 1 ratio. Again, even though we're using a different shape, you also see that surface area to volume ratio increases with a decrease in size. So I soaked these agar shapes in phenolphthalein, or actually no, in sodium hydroxide. There was phenolphthalein, which is a base indicator in the agar, so it changed color as the NaOH diffused into the cube. And after about 10 minutes, pulled the cube out, dried them off, and then I cut them in half so that you could see exactly how far into the agar the NaOH diffused. And so we should be able to do measurements now to figure out what percentage of this cube is now turned pink or has been diffused through, and how much of it has not been diffused. And you do that with your different shapes. So again, some more calculations. Shape number one, actually when you look at these, this is a common misconception. People will say that it diffused into the smaller shapes faster than it did into the larger shapes, but a measurement would actually show that it diffused as far as distance into each shape pretty much the same. It's not going to diffuse faster through the agar of one cube compared to the agar of another cube. It wasn't like it was more concentrated in one versus the other. The difference then is the percentage that got diffused. You can even just see here without doing any calculations that there's a larger percentage of the smaller cube that's turned pink, and there's a larger percentage of the large cube that hasn't turned pink or that hasn't been diffused. So 0.3, 0.3, 0.3, this is talking about the distance that the pink has actually entered into each of these cubes. Total volume that was left white. So what you have to do is you have to think in your head that you need to subtract now from your length of your sides of your cube. You have to subtract 0.3 here because that's turned pink, and 0.3 here, that's turned pink. So you're subtracting 0.6 centimeters from the total length. So we originally started with 3 centimeters across, but now that 0.6 centimeters have turned pink for the volume that's left white, it is now just 2.4 centimeters instead of 3 centimeters. So now when I do volume, I'm going to be using 2.4 as my length by height times width. So that ends up being 13.82 centimeters cubed. Volume of the diffused part, so how much pink was there? Well, you just take your total cube. Let me go back to my picture. You're taking the volume of the total cube, which is what you calculated at the beginning, minus the volume of the cube that's still white. And then what you're left with is how much of that cube actually turned pink. And you're doing that for each of your different shapes. Okay, so we did total volume minus the volume that remained white, and this is how much that was diffused through, and then we want to turn that into a percentage. So amount diffused divided by total volume times 100 to make it a percent, 48.4% has turned pink or was diffused. Shape number two, same thing. You have to subtract 0.6 from the length because again, it went in 0.3 this way, 0.3 this way. So now it's, instead of it being 2 centimeters across, you have to think about it being 1.4 centimeters across. Plug that in, do your subtractions from the original volume, 65.7%. Same thing with the smaller cube, 93.6% of that actually was diffused. And so you can think about the fact that there's only this much and you've got 0.3 going in 3D all the way around the cube. All right, cylinders, same thing. So this is just kind of a visual. I cut these cylinders in half. And again, just like the squares, it went in 0.3 centimeters for both the small cube or small cylinder and large cylinder. This is one cut lengthwise so that you can see that it's going in on the sides of the cylinder. It's also coming in from the top of the cylinder and the bottom of the cylinder. So we have to remember that when we think about how radius and height have changed. All right, so distance diffused again, 0.3, 0.3. Total volume that was left white. Okay, with volume on cylinders, you are taking pi r squared h. Well, for the white, your r has to now subtract or show that you've taken away 0.3 from the radius. But you've only taken away 0.3 from the radius. If this was that diameter all the way across the circle, you would have to take away 0.6 because there's 0.3 here and 0.3 here. But because this is radius, you only lost 0.3. But when it comes to height, like when you're calculating surface area for cylinders, you have to consider the fact that you have 0.3 going in from that way and you have 0.3 going in from that way. So you have to actually take 0.6 off of the height when you're calculating how much of it is still white. And so then Similar to before, take your original volume minus the total volume that's still white, and then do your percentage. The smallest cylinder, you can see that there's actually no white left. So it actually diffused entirely through the whole thing. So 100% of it. All right, again, look at that. As your shape gets smaller, you have a larger percent that has been diffused through. Why does this matter? Well, this can maybe explain to us why, whether you're a redwood tree or a shrew, it doesn't really matter how large you are, you're still going to have roughly the same size cells. And thinking about diffusion, if a cell has to bring in oxygen, it has to have water that enters, it has to ship out proteins, it has to ship out waste, you're going to be a lot more efficient shipping things in and out of a smaller shape that has a large surface area to volume ratio versus a large shape that has a large volume, it has a small surface area to volume ratio. And so surface area to volume, that also matters when it comes to some different adaptations that organisms use, and that's what we're going to talk about right now.